For this video, we're going to have a review of some basics of trigonometry. So let's just start off our review with refreshing our memory on the definitions. So recall if we have a triangle, a right triangle like this. So here is a right angle here. And this angle here is theta. Let's call this side length A, this side length B, and this side length C. So recall we define the sine of theta. This is going to be the opposite side over the hypotenuse. So the opposite side here is B, the hypotenuse is C. Cosine of theta is going to be the adjacent side over the hypotenuse. Adjacent side is A, hypotenuse is C. And then tangent of theta is sine over cosine, which is opposite over adjacent. So this is B over A. So those are our basic definitions of our trig functions. We also have cosecant, cotangent, and secant. So just as a refresher on those, we won't spend much of any time in this video on these. This is 1 over sine theta. So if we look at our sine theta above, we just flip this over. So this is C over B. Secant of theta is 1 over cosine of theta. So we flip this over, so it's C over A. And then cotangent of theta is 1 over tangent of theta. So this is A over B. So those are our basic trig functions that we'll be working with. Like I said, the first three are the ones we'll spend pretty much all of our time in this lecture on. So we can also graph these. And so it's a good idea to make sure we remember the basic graphs for the different trig functions. So let's start with graphing sine. So we're going to start here. We'll go up, down, and up, and then same thing in the other direction, like this. So this top value here is 1. The lowest it can get is -1. Shoot, so I got to fix that graph now. So the lowest it gets here is -1. And then the values here, sine's its biggest here at pi over 2. This is pi. This is 3 pi over 2. And then this is 2 pi. And then we have the same thing just in the negative direction. So minus 3 pi over 2, and then this one's minus 2 pi. So this is y is equal to sine of x. So just remember, this starts at 0, it goes up, and then it continues to go down. We're going to talk about finding the values at some of these angles and some other ones in a little bit. So that's our graph of sine. Let's go ahead and graph cosine now. Let's go to the next page. So for cosine here, so this time we start at 1 and we're going to go down and then come back up. And same thing in the other direction. Come back up like this. And this value here is at 1. The lowest value we get is at -1. And now maybe let's use a different color this time to give our values. So this value here is at pi over 2. This is at pi, 3 pi over 2, and then this value here is at 2 pi. And then similarly in the other direction, minus pi over 2, minus pi, minus 3 pi over 2, and then this one is minus 2 pi. And so this graph here is y is equal to cosine of x. So finally, let's go ahead and graph tangent. So this one's going to have asymptotes. Since we remember that tangent above, we define this as sine over cosine. Anywhere where cosine is 0, we're going to get an asymptote. So notice cosine is 0 here at pi over 2, 3 pi over 2, minus pi over 2, and minus 3 pi over 2. And then, of course, lots of other values as well, but just in terms of what we graphed, those are the values. So let's go ahead and add those to our graph right away. And so we'll put dashed lines here, where our asymptotes are going to be. So remember, this is at pi over 2. This is at 3 pi over 2. I have one here at minus pi over 2 and minus 3 pi over 2. And then if we graph our tangent function, it's going to have an asymptote here. It's going to come up, go through at 0 because sine of 0 is 0. Similarly, we're going to go up like this. Like this. So this is y is equal to tangent of x. Okay, and these intersection points here, these are where sine is equal to 0. So if we look above, that's going to be at pi, at minus pi. So looking above here where the sine is 0, so it's at the pi, minus pi. And then, of course, if we continued out to 2 pi and so on, we'd have values there as well. So as I mentioned, we can go ahead and we want to know the values of these trig functions at some specific angles. Now from our definitions above, if we look back up here, we can see if we know what sine and cosine are, then we can get all the rest of the values, because we can get tangent by dividing those, we can get cosecant by looking at 1 over sine and so on. So we really only need to know how to figure out the values of sine and cosine. So what we're going to do is we're going to learn a little trick here. So we're going to start here with our values of theta. And so the values we want to know are 0, pi over 6, pi over 4, pi over 3, and pi over 2. And if we know those values, then we can use the unit circle, as I'll show you in a minute, how to get the rest of the values. Now what we're going to do is a simple counting. So I'm going to look at square root of 0 over 2, square root of 1 over 2, square root of 2 over 2. So notice I'm just counting up from 0, 1, 2, 3, and square root of 4 over 2. And now notice if we simplify these, this is 0, this is 1/2, this stays square root of 2 over 2, this stays square root of 3 over 2, and this just becomes 1. So all we did was count up with the square roots from 0, 1, 2, 3, and 4 all over 2, and then we'll make another column going the opposite way, so counting down. And now we just need to figure out which column goes with cosine and which column goes with sine. Well, we saw above here, if theta is equal to 0, then sine is equal to 0. So this column must be my sine value, and this column must be my cosine value. And so just by remembering this little chart, this allows us to remember all of the relevant values. And now we can use the unit circle to get the other values. So suppose we want, say, cosine of 3 pi over 4. So what we can do is we can make our unit circle. And remember, our x values are our cosine values. So if I were to think of a theta here, remember this value here is cosine theta, because we think of a triangle, sine theta. So if I look at where 3 pi over 4 is on my unit circle, make my unit circle here, 3 pi over 4 will be over here. So this is 3 pi over 4. But what we can notice is this angle then is pi over 4. So thinking of this in terms of the symmetry here with our unit circle, if we're looking for the value here, where this is pi over 4, we can use the value over here where we know is pi over 4, and we can see the y values are going to be the same, and the x values will be negative. So we have cosine of 3 pi over 4 is negative cosine of pi over 4. So this is negative square root of 2 over 2. And sine of 3 pi over 4, since this is the y value, we see this is the same as sine of pi over 4, which is square root of 2 over 2. So basically, if we know this table up here, which we got just from counting and knowing a single value of sine, then we can use this unit circle to figure out all of the other values we might be interested in. So now one thing that might be different when we're looking at trigonometry and calculus, for opposed to just looking at trigonometry overall, is in calculus we always work with radians. And there is a reason for this. If you use degrees when you're working out certain formulas called the derivatives of sine and cosine, they'll actually scale differently, and you'll have different derivatives if you work with degrees. So we always just work with radians. So let's recall what radians actually are. So again, back to the unit circle, figures very prominently in trigonometry. So what I'm going to do is I'm going to draw the unit circle here. So this thing has radius 1. And so what we have is, if I take and draw an angle here, obviously I'm drawing this much bigger than what it would be. If this is 1 radian, what that means is that this arc length should be equal to 1. So that's how we define the radian. It's the angle so that the arc length there is equal to 1. So we can use this now to relate radians and degrees. So if I go all the way around, so going all the way around would be 2 pi radians. And that would give me the arc length of 2 pi, which is the whole circumference. But this should also be 360 degrees to go all the way around. So if I divide then, that says 1 radian is 360 degrees over 2 pi, which is 180 degrees over pi. So that's how you convert. So this is the formula you use to convert between radians and degrees. Now I did say we're always going to use degrees or use radians in calculus, but sometimes problems will be presented in terms of degrees, so we do need to know how to convert back and forth between the two. And one other nice formula to remember that goes along these lines as well, that might come up, and hopefully you've seen it before, but if not, that's fine, is if I draw a circle here again, but now I'm not saying this is the unit circle. So now let's say this circle has a radius of r. Now if I take some arc length, so if I say this is theta here, this arc length from here to here, this is now r theta, is the arc length. So this might come up later in our study of calculus. So again, more with the unit circle. Like I said, unit circle is very prominent here. We kind of already drew our triangle above that went with the unit circle. So if this is at 1, if I draw a triangle here and say this is theta, this side length is cosine theta, and this side length is sine theta. So if we draw this over to the side, so this is 1 because it's the radius. This is sine theta. This is cosine theta. So then we can just use Pythagorean theorem Remember, that says the base squared times the height squared is equal to hypotenuse squared. So I have cosine theta squared plus sine theta squared is equal to 1 squared. Or another way to write this is cosine squared theta plus sine squared theta equals 1. So this is an important formula that will show up quite often. So it's one of the few trig identities that you should memorize. There's lots and lots of trig identities, but this one we actually want to remember. So now let's get into some other properties of the trig function. So let's note from our graphs above, if I take any angle at all, if I look at cosine of theta and I add 2 pi to that, that doesn't change cosine at all. And same thing for sine. So this means we call these functions periodic because if we go a certain distance, we get the same function back. So we call sine and cosine periodic. And the period here is 2 pi, because that's how far we have to go to get back to where we started. So if we look way back up at the graphs above, notice if I start here at 0, once I get to 2 pi, I've gone all the way through and I'm going to start the same graph over again. Same thing with cosine. So so that's our period. Now the amplitude is basically the height, the distance between the highest and the smallest part divided by 2. So the amplitude is, say, 1 plus 1 divided by 2. So it's 1. So we think of basically if you go from the kind of symmetric line where the y value is 0, we go up by 1 or down by 1 to get the highest or lowest value. So in terms of language, we say any graph that looks like, so say that any graph in the shape of sine or cosine is referred to as a sinusoidal function. Okay, so let's see some ways we can actually transform our functions to make them fit various situations a little bit better. So let's set, say, f of t to be a sine of b times t, and g of t to be a cosine of b of t. And let's see what this a and the b do. So if we look at the absolute value of a, this is the amplitude of f and g. So we can think of, in the cases we looked at already with just sine and cosine, it was just 1, which is exactly what the amplitude was. And now the period, we've put that b inside, so that changes the period. So this is given by, we take 2 pi and we divide it by the absolute value of b, and that's our period. A couple of other things we can do is if we replace t by either t plus h or t minus h. Say we look at, say, a sine of b times t minus h. This just shifts the graph, say, a sine of bt horizontally by a distance of absolute value of h. So in terms of our particular functions, it doesn't matter whether the h is positive or negative here. And finally, the last thing we want to know is if we look at something that looks like a sine of bt plus c, or g a cosine of bt plus c, this c here, this shifts the graph vertically by c units. So this could be up or down depending upon the sign of c. So those are kind of all of the basic things we can do with our sinusoidal functions here. So let's look at an example. Concrete example with some numbers to actually graph that. So let's graph, say, y is equal to, say, 3 sine of sine of 2t. Okay, and let's say plus 1. So the first thing to note is our amplitude. That's this coefficient out front, so that's 3. Now our period should be 2 pi over this b, so this is, our period is just 2, and then this plus 1, we shift vertically by 1 unit. So when I'm graphing these things, I'm going to not label my axes immediately, at least not the x-axis, because it'll be a little bit easier to label the x-axis later. So if the amplitude is 3 and we've shifted up by 1 unit, so let's draw our shift up here. Put a dotted line here where we've shifted it up to. So this is up here at 1 now. Now we know our sine starts at 0, and we know, so it's going to start here because we've shifted up by 1. And since the amplitude here is 3, we're going to go 3 up. And then, so this would be up here at 4. And then if this is at 1, 3 down will be down here at, say, -2. So down a little bit. Doesn't look quite symmetric here, but that's okay. And same thing in the other direction. So something like this. And then we just want to label our axes. So we know the period is pi. So that means this, to complete a full period, we have to go to here. So this value here will be pi over 2. Pi over 4, 3 pi over 4. So this is our function, 3 sine of 2t plus 1. Okay, so the main thing here, if you're given a function like this, just identify where what the shift is to kind of get your red lines, because that's going to kind of be the center of your graph. And then you figure out what the amplitude and the period are, and you can go from there. Okay, so let's try a few word problems now. So kind of see how this material is put into practice. So temperature. Okay, so we're in a desert. The low temperature occurs at 5 a.m. The high temperature occurs at 5 p.m. So there's a 12-hour difference between the high and the low temperature. And so let's go ahead and write a formula. There's lots of ways to do this. We could use sines, we could use cosines, there's ways to shift and whatnot. So let's just pick one of them. A formula that describes the temperature. T, and let's make our T measured from 5 a.m. So that'll make things a little bit easier for us. So for this type of problem, I probably want to start by just doing a rough sketch to get an idea of what's going on. That should help us a bit. So notice we're starting at 5 a.m., and that's corresponding to our T is 0, and we're starting at 40 degrees. And then we know at 5 p.m., we're at a high, so this is at 40. We're up here at a high of 80 at 5 p.m., so it looks something like this. And then it would continue down. If I get back to another 5 a.m., it's going to continue down and look like this. So the highest point is 80. The lowest point is 40, so our amplitude is 80 minus 40 over 2. So this is 40 over 2. So this has an amplitude of 20. And now notice our period is 24 hours. Right, so we start at 5 a.m., we go up to 5 p.m., that's 12 hours, and then another 12 hours to get back to 5 a.m. So this is my A if I'm doing a graph like above. Remember my B, how do we have B? 2 pi over B is the period. So 2 pi over B is equal to 24. Or solving this for B, I get B is equal to 2 pi over 24, or pi over 12. And now a couple of the things we need to do here is notice that the center of this is between these two, which is going to be at 60. The other thing to notice, since we started at a low value, my choice here is going to be to use a cosine. We could also use a sine with things shifted, But in using a cosine, we're going to have to put a negative on it to flip it over. So then my function here, I know I've shifted up by 60. And then this a is 20, but I want it to be negative to flip it. So I'm going to do minus 20. So this makes the cosine start at negative, regular cosine would start at -1 instead of 1. And then I put in my b value, which is pi over 12 t. Okay, so just notice, for instance, if we put t equals 0 in, cosine of 0 is 1, so we get 60 minus 20, which is 40, which is what we're looking for. Okay, and notice this is 12 hours here. So that would correspond to t equals 12, which is cosine of pi, which is -1. So this would be 60 plus 20, which would be 80. So it looks like our graph is fitting pretty good, as it should. Let's try another example now. So we're going to look at the Bay of Fundy in Canada. So this has the largest tides in the whole world. Okay, so the difference between the highest and lowest tides so this is 15 meters, which is pretty huge. So let's say at a particular point, right, so this isn't saying the depth is goes from 0 to 15. It's the difference between whatever the lowest depth is to the highest depth. So let's call that depth y, and we'll measure it in meters. So this is given as a function of time t since midnight by y of t is equal to d plus a cosine of b times t minus c. What we're going to do is we're going to interpret a bunch of these values. So let's start with our first one. What's the physical meaning of d? Well, if we think about when we graph this, whatever the values are, remember the d is what we've shifted it up by. So if we think of this, the d value here is this value up here. So then we'd have a high and a low tide, say, something like this. We don't have to be precise for this part. So in this case, the d is measuring is the depth of water halfway between high and low tide. All right, so here would be our high tide, here would be our low tide. That d is right in the middle of it. Okay, so let's ask, what is the value of a? Well, remember, a here is our amplitude. So the problem gave us the difference between the highest and the lowest here was 15. So that means a is 15 over 2, which is 7.5. Okay. So what is the value of b, assuming the time between high tide, between the two high tides is 12.4 hours. So if we're talking about the time between the high tides here, something like this, say, that's this distance here. If this is 12.4, then that means my period is 12.4 hours. So my period is 12.4, and I know that's 2 pi over b. So we solve this for b, and b is equal to 2 pi over 12.4. And finally, the last thing to ask, let's make sure it's clearly a C. The last thing we might ask is, what is the physical meaning of C? Well, when we look up at our equation, if we remember from before, this C here, this shifts things horizontally. Okay. So depending on the sign of A, the value of C is the difference in time between high tide, if A is bigger than 0, and midnight, or low tide, if A is less than 0, and midnight. Okay, it's just shifting, because normally you'd want t equals 0 to be our if A is positive, t equals 0 would what we'd want to be our high tide, but in this case, if I plug t equals 0 in there, I don't necessarily get that cosine is 1, but if I shift it and I plug in t equals c, I get cosine of that is 1, so then it's either positive or negative here, depending on our A value. Okay, let's try one more example. So you can see these sines and cosines can model lots of different things. And so it's important to understand what the terms in your model are actually telling you. Okay, so the depth of water in a tank is going to oscillate sinusoidally once every 6 hours. So our lowest depth is 5.5 feet, and the largest depth is 8.5 feet. Let's find a formula for the depth in terms of time t measured in hours. So here we're not told what time of day or anything, so we can make that choice ourselves. So again, let's do what we did before, and let's start with the possible graph of this. So we know the highest and lowest values, and we can go ahead and let's assume we're going to start and we're going to go up and then down and then back up again. So this value here is going to be our shift up. The highest point here is 8.5. The lowest point here is 5.5. And again, they didn't tell us in this problem we didn't have to decide t relative to anything else. We could make our own determination of this. This value here will be my c. So notice the amplitude here. Remember, this is a rough sketch. I haven't put any labels on the t. This is just to help us figure things out. So this is 8.5 minus 5.5 over 2. So this is 3/2. And then my period, we said, was 6 hours. So this distance from here to here, this is 6. So this is 6, and this should be 2 pi over b, which means b should be 2 pi over 6, which is pi over 3. And then we notice that c is right in between here. So if this amplitude here is 3/2, then c is 5.5 plus 1.5, which is 7. So when I go to write my graph, then I can write f of t. I know I've shifted up by 7 because that's my c. My amplitude is 3/2, and then we've drawn this as a sine function with a period of pi, or the b value here is pi over 3 with a period of 6. So this is my function.